In this video, we're going to take a look at the characterization of AC voltages and at the conversion from AC voltages to DC voltages using rectifiers like a half-wave rectifier or a full-wave rectifier. Here is an example of a sinusoidal AC voltage specified by A times sine 2 pi ft. So two of the parameters in here are A and the amplitude and the frequency f. The period of this waveform goes from here to here and is equal to 1 over f. And then we can look at different characterizations using the amplitude of the waveform. A simple one is to just simply look at the peak voltage, so that is the main excursion from 0 to the maximum voltage, either positive or negative, so this would be Vp. Then we can look at the peak-to-peak voltage, so we can look at the bottom and at the top of this waveform, and then in between is the peak-to-peak voltage. Then we could look at the average of the voltage, so that is defined here by this equation. So we just simply take the average over one period and then divide by the length of the period. In the case of the sinusoid up here, it is clear that the area under the positive peaks and under the negative peaks is the same, so the average voltage would be 0 for this kind of sinusoid. And then we could also ask what happens if you would take a sinusoidal voltage like that and apply that to a resistor, and how much power that would deliver to the resistor, or to ask it differently, how hot the resistor would be getting from applying such a sinusoidal voltage. And in this case, we need to look at something that's proportional to the voltage squared. Okay, so that's this quantity here, magnitude squared of the voltage, and then we integrate over one period again and divide by the length of the period. So that inside here would be average power, and then we take the square root of that, and that gives us the root mean square voltage, or VRMS. For sinusoidal voltages, the VRMS value, if we know what the amplitude of the sinusoid is equal to A over square root of 2, or 0.707 times A. And just to mention that here, transformer voltages are usually given in volt RMS. Or for example, if you talk about 120 volts AC, the line voltage, that's also a VRMS voltage. And the corresponding A would then be the 120 times the square root of 2. So that would be square root of 2 times 120. That's approximately 170 volts. Now we are interested in converting an AC voltage like this input voltage here into a DC voltage. And the simplest case is to just use one diode in the pass from the sinusoidal input to the load. So this diode will only conduct during the positive half of that sinusoid, and during the negative half it will be blocking current, and so we get an output that looks like this. We just have the positive halves, the negative halves we have 0, then we have positive halves again, and 0, positive halves. The period here is 1 over f, and we assume that Vs of these A times sine 2 pi ft, so we can compute from this our various quantities, peak voltage, peak-to-peak voltage, and so on. Peak voltage is easily seen from the picture here to be just A, and because we don't have any negative voltages, that's also equal to the peak-to-peak voltage. The average voltage is the integral over A times sine 2 pi ft dt from 0 up to t, and then divided by t. And if you carry out this integration, you find that this is A over pi, and that's approximately 0.318 times A. And the VRMS voltage, so now you're taking the sine squared here, so A times sine squared 2 pi ft dt, integrate over that from 0 up to t, divide by the period, and then take the square root of it. And use the trigonometric identity that the sine squared of 2 pi ft is equal to 1/2 times 1 minus the cosine of twice the frequency, so that's 4 pi ft. And then it turns out that the integration over the cosine 4 pi ft gives the 0, and we're just left with the 1/2 in here, and that's how we get then an A over 2 for the RMS voltage, which is equal to 0.5 times A, where A is again the amplitude of the sinusoid. Just as a note, here VPP, the peak-to-peak voltage between top and bottom, that's also called the ripple voltage in the connection with power supplies. So the next interesting question is to see how could that ripple voltage be reduced. The ripple voltage in the previous slide was just equal to the amplitude of the sinusoid, and that is not very satisfactory for a DC power supply. So we introduce a capacitor here, which acts essentially as an energy reservoir during the times when the negative half of the sine wave is coming in and the diode is not conducting. So what we are getting is we start somewhere here at the peak of the sinusoid, and then we get an exponential decay from here, because the C and the R here, they form an RC pair, and the discharge of a capacitor through a resistor has a negative exponential decay. And then when the diode conducts and the positive half cycle is here, then the capacitor gets charged up again, and then it keeps discharging and charging up and so forth. And so depending on the time constant, so we have here a time constant, which is RL times C. Depending on how large this time constant is, that decay here, that exponential decay, goes either faster or slower. It goes faster if the time constant is small. It goes slower if the time constant is large. And so we can control the peak-to-peak voltage that we get between the top here and the bottom here. So that's the peak-to-peak voltage indicated over there. To figure out how to compute that peak-to-peak voltage, dependent on the time constant, we need to take a look at the time when the capacitor is being charged and the time when it is being discharged. So for charging, we go from here when the exponential decay is hitting the next positive half cycle up to the top of that half cycle. And when you look at that, that's approximately 1/4 of the period, and the period here is 1 over f, so we have about 1 over 4f for this time. And then the rest of the period, the capacitor has to deliver the energy, and so we have here 3 over 4f as being the time approximately when the capacitor discharges. So that's noted down here. Capacitor charges during about 1 over 4f and discharges during about 3 over 4f. Those are not exact numbers, but they come reasonably close for peak-to-peak voltage ranges that are of interest for power supplies. So now, because the discharge of the capacitor through the resistor has a negative exponential form, we can write that the peak-to-peak voltage or ripple voltage is equal to 1 times A minus e to the minus 3 over 4 F RLC, where the 3 over 4 comes from the fact that we had about 3/4 of the period discharge of the capacitor, and then RL times C is the time constant, and we basically have to compare that time constant to the frequency, essentially looking at how much of a period for a given frequency that time constant is equal to. And because a small exponential like e to the minus x for small x is approximately 1 minus x, we can use that in the formula up here. So the one here cancels, and we're actually just left with the exponent here. And that is approximately 3a over 4f RLC for the value of the ripple voltage. And another quantity that's important for the design of power supplies is the minimum voltage that we are getting here. So that would be, if we look at the bottom of the ripple, so that's V minimum V of t, and that's the lowest voltage that we are going to see, and it has to be higher than the output voltage that we would like to produce with a power supply if this is going to work well. So that minimum over all t of V of t is equal to Vp minus Vpp, and that then becomes e to the minus 3 over 4 F RLC. Again, that is a consequence of the discharge time being approximately 3 over 4 F, then times A. And if we use the approximation from up here, which is true for peak-to-peak voltage much less than the peak voltage, then we get 1 minus 3 over 4 F RLC times A. So that's the bottom of the ripple voltage, and for a linear regulator this has to be larger than the desired output voltage plus the minimum voltage drop across the regulator. To improve the efficiency of the AC to DC conversion, we can use a full wave rectifier, and that uses 4 diodes. So we're going to take a look at how current flows through here during the positive half cycle and during the negative half cycle. So during the positive half cycle, we have current flowing here through this diode, and then it flows through the load resistance here, and it flows back through the diode down here, and then out through the transformer winding or the battery. That would be here at the input or anything similar. If we have a negative half wave like this, or negative voltage that comes in, then the current is going to flow in the other direction. And so we can look at it here. For example, it's going to flow out. So that is not going to come from this diode, but it's going to come through this diode here. So it would flow out this way. And then we have current flowing. Okay, so this arrow here is not correct. We need to remove that. Okay, so it's flowing out here. It could not flow through here because of this diode here, but it's flowing out through this diode here. Okay, and then we can go back and look at the load resistance. So it's flowing in this way through the load resistance and then goes out here. and then coming in, it flows through this diode in this direction, and it flows from here in this direction. So you can see that now on the input side of the AC to DC conversion, it flows in from the bottom, goes here to the top, and then moves through RL, and then comes out through the bottom and up into the top here. So at the AC side, current can flow in either direction depending on whether it's a positive or the negative half wave. On the DC side, however, it flows in the same direction for both of them. So we produce a DC current here because it only goes in one direction. So the input voltage is typically A times sine 2 pi ft, and then the output voltage V of t is just the magnitude of A times sine 2 pi ft. So whatever negative voltages we have at the input, they get flipped up. So if we look at this drawing here, so this part came from the positive half wave, this comes from the positive half wave, and this comes from the positive half wave. And then the ones in between come from the negative half wave at the input. One of the things that you notice here is that the period of the DC waveform is only 1/2 of the period of the sinusoid at the input. So it's 1/2f is the period. So if the input is 60 Hertz, for example, then we actually get a frequency, a fundamental frequency of 120 Hertz here at the output. Looking at the peak voltage, it's easy to see that the peak voltage is equal to A, and it's the same as the peak-to-peak voltage as actually in the case of the half-wave rectifier. So that's shown here. That's also equal to the ripple voltage. The average voltage is now twice as much as it was for the half-wave rectifier because we use both the positive half-wave and the negative half-wave at the input. So that's 0.637 times A. And the RMS voltage is also going to be larger. It is now A over square root of 2, which is approximately 0.707 times A. Just as we have seen for the half-wave rectifier, it's possible to reduce the ripple in the output voltage by putting in a capacitor that acts as energy storage during the times when we have the zero crossings of the input sinusoid. Okay, so we are starting at the top of the sinusoidal waveform, and then we get this exponential decay. Then we charge up the capacitor again, we go have exponential decay again and charge up again, and so forth. And when you look at the timing of this, you can see that from here to here we are discharging, and then from here to here we are charging. So this is charge, and here is discharge. And compared to the period, which goes from here to here, we can see that we have about 3/4 of the period, and the period here is 1/2f, so it's 3/4 times 1/2f of the time for the discharge, and we have 1/4 times 1/2f for the charge time. Okay, so this is shown down here. The capacitor charges during approximately 1/8f seconds, and it discharges during approximately 3/8f seconds. And similar to the case of the half-wave rectifier, the decay of the voltage when the capacitor gets discharged through the resistor is exponential, and so we get 1 minus e to the minus 3/8f RLC And RLC, again, is the time constant. And that whole thing is multiplied by A. And if we use again the approximation for a small exponent, we get approximately 3A over 8F over RLC for the ripple voltage or the peak-to-peak voltage. That is true if the peak-to-peak voltage is much smaller than the peak voltage. As a rough idea, you would like the peak-to-peak voltage to be probably 20% or less of the peak voltage for this formula to be a good approximation. And finally, the minimum of the output voltage is equal to Vp minus Vpp. That's approximately e to the minus 3 over 8 FRLC times A. And if Vpp is much smaller than Vp, this becomes 1 minus 3 over 8 FRLC times A. And that again is the design voltage that you need for designing power supplies. It's the minimum voltage that you will have available at the input of a voltage regulator, for example.